Good day everyone, and welcome to another tutorial on Programmation, functionelle, Calculabilite and computability. If you're just joining us, there are 3 videos. Probably you find them below, or you can check the link, the description below this video. It's introduction to Calculabilite / computability. There are 3 videos and they will lead you to this particular video. So for Regle minimisation, just like we defined Regle composition and Regle recursion, G is a function of arity n plus 1. In this particular case, it's between, there is no H, it's between G and F. Okay, so we are going to construct F from G, just like we did for Regle composition, Regle recursion. Just in those cases we had H, but here that we don't have H, okay, I'll give you the definition. Let's say given ou bien soit G a function of arity n plus 1. So G is a function of arity n plus 1 such that for every x1, x2 up to xn, that's for all the variables that we're treating natural numbers. So for every variable that we'll find in natural numbers, so it's of arity n, because see, I'll write it down, like given a function of arity n plus 1 such that for every if I don't put it as for every, I'll basically just use this putut for every putut x1, x2, x3 jusqu'à xn appartient à n puissance n. By now we already know what this means. It means it's of arity n, and that means F is of arity n. So for every x1, x2, x3 up to xn, there exists at least an y such that there exists, sometimes if I don't use there exists, I'll go ahead and use this. So that's il existe at least an y, at least y, just do that, so in n as well, such that, now this is the definition I'm going to give us now, such that G of x1, x2, x3 up to xn and then y will be equal to 0. So this is the formula, this is the definition. So giving G a function of arity n plus 1, so G is a function of arity n plus 1, such that for every x1, x2, x3 up to xn in natural numbers, there exists at least y in n such that G of x1, x2, x3 up to xn and then y is equal to 0. Sorry. So it means la fonction d'arité n is said to be constructed by this Regle minimisation from G if it is defined as follows. Use a black pen. So that means we're using lambda notation. For those of you are just joining us as well, we already explained the lambda notation in the first video, so maybe you can check it as well, or I'll just put it here as well. So my function f of arity n Remember, we're going from n raised to the power of n to n. So that means we're having x1, x2, x3 up to xn. The mean of y slash j x1, x2, x3, xn, y equal to 0. So using the lambda notation, it would be f is equal to lambda x1, x2, x3 up to xn mean y g x1, x2, x3, xn y not 0. So this is how we define the Regle minimization. I know it might be looking a bit confusing for most of us, but I'm going to give an example that will actually explain this. It just basically means there exists like an y, a y, like there exists an y such that the function g will be equal to 0. Remember, we're dealing with natural numbers, so even if I get an answer, maybe in the example will be maybe even if I get an answer of 0.569, maybe we only take the natural number there, which is 0. We don't have anything to do with the decimal, the shift the numbers after the decimal point. So that's Regle minimization. So we should find an y, or maybe you might even be given another variable, maybe z, which we'll see in our example, such that when we do the calculation, we'll get 0. The natural number from it will get 0. That's Regle minimization. So let's do an example. Soit la fonction définie par g x y z, or since we are used to the notation x1 x2, we'll use x1 x2, and then in the place of z we'll call it y. So we'll do this x1 x2 and y. Then the definition of this function is this: x1 plus x2 all over y plus 1. So we'll be given the values of x1 and x2, and we'll be asked to find z and find y such that g of x1 x2 y will be equal to 0. So let's say x1 is 2 and y is an x2. I was using x, y, and z. So if x1 is 2 and x2 is 3, it means that g of 2, 3, and y, okay, you see, so we have x1 and x2, so we put in the values 2 and 3 here, so it will be 2 plus 3 over y plus 1, which will give us 5 over y plus 1. Now the astuce now is we should think, what is the value of y that I'll put here that will make this function to be equal to 0? Remember, we're in natural numbers, so we are only picking the natural numbers. Like, what number, starting from what number do you think we will put here that will give us 0, that will make this function equal to 0 as Regle minimization quote? Now if you look closely, you would see that if I put y equal to 5, I'll be having 5 over 6, and that's where it will start being 0, because if I put y equal to 1, I'll have 5 over 2 and I won't get a 0 point something. Or if I put 5 over 2, 5 over 3, 5 over 4, I will get a 1 point something. So it's at the moment I put in y equal to 5, you see, I will now have 5 over 6 and I'll be able to get 0 point something. And because we're in natural numbers, we're picking only the whole numbers, so we pick only the 0. That's how Regle minimization works. So it means that there exists y such that 5 over y plus 1 will give us 0. So we know what our y is supposed to be now. It's supposed to be 5, and that is y is now equal to x1 plus x2, right? So y is equal to x1 plus x2, which in this case is 2 plus 3, and to give us 5. And in that case we'll get our function to be equal to 0. So from here we've been able to construct f from G using Regle minimisation. Like I said, because the only way we can start having a 0 in this our particular function is when we put in x1 plus x2. So it's by having y equal to x1 plus x2 in this particular question. So I think I'll just stop this here, so that in the next video we'll go into what is when do we say a function is primitive recursive, and when do we say a function is recursive. And then we'll be dealing with the derivation of recursive functions, and then we'll start answering exam questions under this. So you should check in the link in the description below, or just down there, and you'll find the next video following this. Thank you, and see you in the next video.